In this section, we're going to look at differential equations, and the first thing we're going to talk about is understanding what a differential equation actually is. There are three things you can look at. The first thing is that the equation contains at least one derivative. For example, y prime of x. The solution is a function, y equals f of x. So we start off with an equation with y prime. We want to solve it to end up with y, the original function. And the third thing is the order. The order is that of the highest derivative. This is y prime, which is a first derivative. We could have y double prime. What we do is solve differential equations that are just first order, but in this section we will look at some that are of a higher order. Remember, the first derivative is the rate of change, at which the output changes with respect to the input. So if I have a function y equals f of x, y and f are the output letters, and x is the input letter. So let's look at a few differential equations, and we're going to also look at how a solution works in the differential equation. Our first example to look at is the differential equation x squared y prime minus 4x squared y equal to 2xy minus y prime. It's a differential equation because we have two derivatives in it, at least one. Is 4x squared a solution? Now, this just says 4x squared, but remember that we have y prime, so really we want to test to see if y equal to 4x squared is a solution, because a solution has to be a function. So this is f of x equals y equals 4x squared. In the equation, I have a y, so what I'll do is substitute 4x squared in place of y, and I also have y prime, so I need the derivative. So y prime is equal to 2 times 4 is 8x. So I take the derivative, and now I go back to my differential equation and plug in. I have x squared times y prime. Y prime is 8x. Minus 4x squared times y. Y equals 4x squared. And the question, does that equal this side of the equation? We're testing to see if this 4x squared is a solution. So I have 2x times y, which is 4x squared, minus y prime, which is 8x. And I work on one side at a time. So over here, I have x squared times 8x is 8x cubed, minus 4x squared times 4x squared, 16x to the fourth. Is that equal to 2 4s are 8, x times x squared is x cubed, minus 8x. These are not the same. So, no, y equals 4x squared is not a solution. Let's look at a different example. Derivatives. 1/4 comes around front. I subtract 1, which gives me negative 3/4. And then by the chain rule, the derivative of the inside is 2x. I'm just going to leave that as a derivative and see how it fits in with our differential equation. Differential equation is y cubed equal to. So I take y here, x squared plus 1 to the 1/4, and I raise it to the third power. And then I multiply it by y prime. So all this is y prime. I think I'm going to combine the 2x and the 1/4. And then I have the part with the power left. X squared plus 1 to the negative 3/4. Finally, at the equal sign, does that equal x over 2? Okay, let's see. Now, I have x squared plus 1 to a power to another power, so these two powers multiply, rule for exponents. 2x over 4, I can write that as x over 2. And I have x squared plus 1 to the negative 3/4. And if you'll remember, x squared plus 1 to the 3/4, x squared plus 1 to the negative 3/4, same base. So you can add exponents, and 3/4 minus 3/4 gives you 0. So this whole piece right here actually becomes 1. Something to the 0 power times x over 2 is equal to x over 2. So since this is something to the 0 power, which is 1, this is true. So we say yes is the solution. The problem we're looking at this time is y of x equal to 3x cubed plus 1 over x squared. A solution to x squared times y double prime of x minus 6 times y of x equal to 6 over x squared. Be very careful with this notation because it is y of x. So when you see something like this in a differential equation, it does not mean y double prime or y prime, whatever, multiplied by x. You could have y squared of x. Now that would be y squared, whereas this is y double prime. That's different. This is y of x quantity squared. So watch out for the difference between your derivative notation, prime and double prime, and your powers, because these two are totally different. And in both cases, the x is not a multiplier, it's function notation. And here we have y double prime. So this is our y, and remember that 1 over x squared is x to the negative 2. So if I want to find y prime of x, I'll take the derivative, 3 3s are 9x squared, plus, and I need the derivative of x to the negative 2. Negative 2 comes around, times x, subtract 1 gives me negative 3. So this is y prime. Y double prime, the derivative of that, 2 comes around times 9 gives me 18x. Here I had minus 2. I'm going to continue it just within this parenthesis. Negative 3 comes around times negative 2 gives me 6. X, subtract 1, now to the negative 4. So I've got y prime, I've got y double prime. This is my differential equation, and so this is the one I'm trying to determine whether or not this y is a solution to this differential equation. So let's come down here and see where we are. All right, I've got x squared times y double prime, which is 18x plus, and I think I'm going to go ahead and make this 6 over x to the 4th. Put it back as a fraction. Now that's this piece, minus 6 times the original y of x. Up here, 3x cubed plus 1 over x squared equals 6 over x squared. That's what we're trying to determine. X squared times y double prime minus 6 times y equals 6 over x squared. I didn't use the y double prime in the equation. I just needed, the y prime in the differential equation. I just needed to get that to get to the second derivative. So let's see. If I distribute my x squared, I have 18x cubed plus 6x squared over x to the 4th minus 18x cubed, distribute the minus 6 over x squared. Does that equal 6 over x squared? Let's see. I have 18x cubed and 18x cubed that cancel. 6x squared over x to the 4th is actually 6 over x squared. I can simplify that part. minus 6 over x squared equals 6 over x squared. Well, that's not true. This side's 0. So that's not true. So this is not a solution. It could have been, even though it's y double prime, this could well have been a solution if I'd had something a little bit different here. Because it almost looks like when I get this term, it's going to work. And it doesn't. You really have to work all the way through your problem. Be very careful with exponents and all your cancellations or whatever happens. Addition and subtraction, signs are critical to determine whether or not you have a solution. In this part, we'll do the very first solving of differential equations. Now, these are very basic ones, which means that it's an equation that can be rearranged and written as y prime equals some function g of x. We use just integration, basic integration, although sometimes use substitution to solve it, but it is integration where we take the antiderivative of y prime dx. Remember, y is a function of x, so it's the integral dx, equal to whatever y prime is, which is some other function g of x. And when you do the antiderivative of the derivative, you get y. And the antiderivative of little g would be capital G of x plus c. And sometimes you have to find c, that you will be given an initial condition, and you'll have to find what the constant of integration is equal to. So let's look at one of these types of problems. We have the equation 5e to the x times y prime equals e raised to the 2x power minus e to the x. And we do have an initial condition where if x is equal to 2, y value is equal to 4. But this is not in the form I said of a basic differential equation where we could set it equal to y prime. To get y prime, we have to divide everything by 5e to the x. So I divide over here, it goes away. Over here, I have e to the 2x minus e to the x. And I can divide the whole thing by 5e to the x. But what that really means is dividing each piece by 5e to the x. Because I need it in simplest form so I can actually find the antiderivative. So y prime is equal to, if I have the same base, I can subtract exponents. So I have e to the 2x minus the x gives me e to the x on top with the 5 on the bottom. Okay, 5 does not change. Minus over here, e to the x over e to the x cancels and just leaves me with the 5 in the denominator. And so now I need to take the antiderivative. Now the antiderivative of y prime dx is equal to the antiderivative of all of this dx. Antiderivative of y prime is y equal to the 5 in the bottom is a constant. You can think of it as 1/5 as a multiplier if you want to. Antiderivative of e to the x is e to the x minus 1/5 is a constant. So since the variable is x, the rule for antiderivatives with a constant says multiply by your variable of integration. So this is what y is equal to. So we need to find out what c is equal to by using the initial condition. Y of 2 equals 4, x is 2, y is 4. So y is 4 equal to 1/5 e to the x, which is 2, minus 1/5 times x, which is 2 plus c. The easiest way to do is to leave c where it is, because we're solving for c, and move everything else to the other side of the equation. So over here I have 4. I subtract this one, 1/5 e squared. This is subtracted already, so I add 1/5 times 2, which is 2/5. So this is what my c is equal to. This is my equation. I just put c back in place of the c here. So I have y equal to 1/5 e to the x minus 1/5 x plus, and then all of this goes in here. 4 minus 1/5 e to the second plus 2/5. And this is the exact value of the function when x is 2 and y is 4 that fits this specific differential equation. Now sometimes you'll see these written a little bit differently. This is an exact value. Sometimes a decimal approximation works better. Another way you could write it, I could put y equal to 1/5, factor it out, e to the x minus x, plus, and then get a decimal value for this, which is something like 2.92, something like that. So either way to write this differential equation is fine. For this example, we want to find the particular solution for the differential equation t raised to the third power times p prime equals 2t to the fourth minus 4. Now, a particular solution is the wording that is sometimes used when you want to use your initial condition and find the value for the constant c of integration. Now, in this case, we have a p prime here, kind of a funny looking prime. There we go. And t cubed, so p is our function, and the input variable is t. So remember that a derivative is the rate of change of the output variable, which in this case is p, times the input divided by the input with respect to, the input variable t. This is basic differential equations. I need to rewrite this as p prime equals. So to get p prime equals the rest of the equation, I have to divide through by t to the third. So divide each piece separately by t to the third, minus 4 over t to the third. I'm going to do antiderivatives, so I want to simplify this a little bit more. The t's will cancel, and I'm left with 2t on top in the first term, minus, and I bring the denominator up with a negative exponent. That will let me take my antiderivative. So I have antiderivative of my p prime, and this time it is dt, equal to, let's go all the way over here, antiderivative of all this with respect to t. Antiderivative of p prime is p. 2 is a constant multiplier. I use the power rule for antiderivatives. This is t to the first. Add 1 to the exponent, becomes t squared over 2. Get the exponent and then divide by the same thing. Minus 4 is the constant multiplier. Add 1 to this exponent, gives me t to the negative 2, and I divide by the same thing, negative 2, and then plus c. So might want to simplify this a little bit before I try to find what c is equal to. P would equal, these 2's cancel, give me t squared, minus 4, but I have a minus 2 here, and those will cancel and give me plus 2. T to the negative 2, I can either leave it there or put it back in the denominator, and I think I'm going to put it in the denominator, plus c. So this is my function, and I need to solve and find out what c is equal to. Let's go back up here. So p is 7 equal to t squared, 1 squared, plus 2 over t squared, which is 1 plus c. So to solve for c, move everything to the other side. 7 minus 1 minus 2, or I could have added 1 and 2 as 3 and then subtracted. So c is equal to 4. So my solution with the condition met, my particular solution, is p equal to t squared plus 2 over t squared plus 4. And generally, we do want to keep our positive exponents. So this is likely to be the form that you would see it given as a solution. This is another basic differential equation because I have something times y prime, and I can move this piece by dividing to the other side, so I'll just have x's on the right-hand side. So let's do that. If I divide here, my e to the negative x squared goes away entirely. Over here, again, we'll divide each piece separately. X over e to the negative x squared plus 2 over e to the x squared. And when I divide by e to the negative x squared, it just goes in the same denominator. Okay? I definitely need to simplify this before I can find the antiderivative. And generally, it's better not to have an exponential with a negative exponent in the denominator. Remember what the negative exponent does, it moves it to the numerator with the positive exponent. So I have x, and then what comes up is just e to the positive x squared. Over here, I have two things with the same base, and if I add exponents, x squared minus x squared is 0. E to the 0 is 1. So my denominator here, e to the 0 is 1. So this is just plus 2. So let's do the antiderivative of y prime. I get y equal to antiderivative of all of this. Now this I'm going to do separately. The first term, integral of e to the x squared dx, plus the second term, integral of 2 dx, because this term requires u substitution. So to work this one out, I need to have u equal to x squared, because we have a rule for antiderivatives, e to the u times du. We take the integral of that. So I need my du. Derivative of that is 2x dx to give me my complete du. And you'll notice that back up here, I don't have a 2. I have the x and the dx, but I don't have the 2. So I'm going to put a 2 in with that x, and then that means I have to put 1/2 in front. So that when I integrate, my y here is 1/2 the integral of e to the u, and then 2x dx is du, plus the integral of 2 dx. I did this separately because I've got this e to the u, and this is just in terms of x. So I like to break those up. So here my y is equal to 1/2. The rule says that's e to the u. E to the u was x squared. Plus the antiderivative of 2. 2 is a constant. You multiply it by the variable of integration, which is x, and then we add c. So I have 1/2 e to the x squared plus 2x plus c. I had an initial condition given. So I do need to find my particular solution and get a value for c. Let's go back up here and plug those numbers in. So if y is -2, -2 is equal to 1/2 e to the x squared, x is 0, 0 squared is 0, plus 2 times x, which is 0, plus c. So let me simplify this before I find c. 1/2 times e to the 0 is 1/2, plus 0, plus c tells me that c is equal to -2 minus 1/2. -2 minus 1/2 is -2.5, which is -5/2, or just -2.5. So to write my function, y I could write as 1/2 e to the x squared plus 2x minus 5/2, because c is equal to -5/2. Or I could write it as decimals. Y is 0.5 times e to the x squared plus 2x minus 2.5. And either way that you write it is correct. Either one of these would be fine. In this lesson, we're going to look at separable differential equations. You've already solved basic ones that were just y prime equal to a function of x, basic integration. Separable differential equations have x's and y's more mixed up, and we have to separate them so they can be written in the form y prime equals, and the first part may have y's in it, a function of y multiplied by the functions of x. So the first example I'm going to do is similar to one in the lesson, but I'm going to mostly do ones that are a little bit different. So be sure to check out the discussion and the examples that are in the lesson. The first equation, y prime equals 4x squared y. So we have the x and the y all mixed up, multiplied together on one side. Remember, they'll be multiplied together. In order to separate the variables, you have to go back and remember what y prime really means. Y prime means the derivative of y with respect to x. So I do have an x and a y on both sides, and I want to separate them. I'm going to keep the dy over here, because usually if it starts off y prime equals, we want to end up with y equals. So the dy stays on this side. I'm going to move the dx to the other side, and at the same time, I'm going to divide both sides by y. So my equation now reads dy over y equals 4x squared dx. Okay, well, let's see what am I going to do now. Take the antiderivative. So if I take the antiderivative of both sides, the left side you could think of as the integral of 1 over y dy, so that it equals natural log absolute value of y plus c1. The right-hand side, 4 is a constant multiplier. The antiderivative of x squared is x to the third over 3 plus c2, different constants. Well, what we want to do now is combine things, and I'm going to go ahead right away and add c1 and c2, or subtract c1, get one constant. So let's go up here, and I have ln, absolute value of y, equal to 4/3 x cubed plus c sub 3. Remember, you subtract constants, you get an additional constant. But I need, for a solution for a differential equation, to have what y is equal to. Now, you are accustomed to having a function e raised to a 0.03 t power, and you have to take the natural log of both sides to get the variable out of the exponent. Now, to get the variable out of the natural log, we do what's called, we exponentiate. We make both sides a power of e. So I have e to the ln of y equal to e to the 4/3 x cubed plus c3. The e and the ln are still inverses, inverse functions. And so over here now, I just have y. And I'm going to assume my y is positive, and I'm not going to worry about absolute values. We have a function y, and anything that we need is going to be on the right-hand side involving the x's. Over here, I can rewrite this exponent. E to the 4/3 x cubed, and then I'm going to multiply by e to the c sub 3. If you think about this, rules for exponents, if the base is the same, you can add the exponents. So if you have a sum in exponents, you can rewrite as two separate functions multiplied with the same base. But this is messy, and this piece is a constant. E is 2.7 whatever, and C3 is another constant. So what I can do is write this as this is a constant, I'm just going to call it C, times E to the 4/3 x cubed. I don't have an initial condition. This is just the function that I have to work with. And so this is a solution. This is the general solution to my differential equation. It's called a general solution because it takes into account every possible C you could have. A particular solution comes from an initial condition where we have to solve for C. But this is the general solution, is the answer to the solution to that differential equation. So we have an application problem in a section about separable differential equations. So we will have to find a formula that we can then separate and solve. The company that we have appreciates in value at 4% of its net worth each year. The payroll is $10,000 each year, paid out continuously. So we have an income, the company's growing, and then we have a payout. The company began in 2002, so that we'll consider T as the time in years since that time. So at T equal to 0, the worth of the company was $300,000. This is our initial condition. What we want to do is find the value of the company in 2010. So we have to invent a differential equation. We need a derivative. A derivative is a rate of change. Income changes 4% of its worth every year. So if W is the net worth, the change in W per time T is increasing, so that's a positive 0.04 times W. Payroll is being paid out, so we subtract the 10,000. So what we have here is income minus outflow, and it is a rate of change. This is a per year thing. So we want to try to find a formula for W where we can then plug in a value that would be 2010, and in 2010, that would be T equal to 8. So we need to develop our formula. Now, for separable differential equation, we are supposed to have a function of the function name, which would be some function of W, multiplied by a function of the independent variable, which in this case is T, but I can't subtract them, so this whole thing has to be grouped together as H of W, and I need something over here. I don't have anything. I'm going to put 1. Because for a separable differential equation, we have to have the function in a function and the variable in a function multiplied. So if I write it like this, I can separate. I can keep the dW here and multiply over by dt, and then all of this will have to move under the dW. So I've got dW over 0.04 W minus 10,000 equal to 1 times dt. Looks very strange, but that's exactly what we have. And the next step is to take the antiderivative. So when I take an antiderivative here, I have to use U substitution, dW over all this. So my U will be 0.04 minus 10,000, 0.04 W. All right, let me try that again. U is 0.04 W minus 10,000. So the du, derivative of 0.04 W, is 0.04 dt. I have to adjust for a 0.04 in here. In 0.04, to go with my dW, and then I'll have to put 1 over it in front. So my integral becomes, go back up here, get rid of that piece, 1 over 0.04 times the integral of 1 over u du. I have the du on top, I have this 1 over u in the bottom, and that equals the integral of 1 dt. So now I've got w's and u's and t's, and I just keep my integration, 1 over 0.04. This is natural log, absolute value of u. I'm going to move that plus c to the other side, equals 1 is a constant, just 1. Rule for integration says if you have a constant, you multiply the constant by the variable, which is t. So when I do my integration, this is what I end up with. And now I have to put the u back to be what u was, this piece down here. Okay. 1 over 0.04 natural log, I'll back up here. 1 over 0.04 natural log of 0.04 W minus 10,000 equals T plus C1. Not too easy for this one. I'm going to need more space here. Okay, here we go. I multiply over the 0.04 first because this is the piece inside here that I'm trying to get to so I can isolate that W. So multiply 0.04 over here gives me ln of all this equals 0.04 T plus, and I'm going to go ahead and multiply 0.04 times C1 and call it C2. And as happened before, if I have an ln, I need to get it out. So I take that as e to that power equals e to that power. And I can write my e to the ln. I'll remove my absolute value so I can account for that elsewhere. My 0.04 W minus 10,000 is equal to e to the 0.04 T, the point, plus C2. Now, e to the 0.04 T plus C2 can be broken up, like we did in a previous example, and this side can be written as C3 times e to the 0.04 T. And I still have this. But I'm getting closer because now I can actually do some recognizable algebra and solve for W. So 0.04 W would be C3 times e to the 0.04 T plus 10,000. And then W is equal to C3 e to the 0.04 T over 0.04 plus 10,000 over 0.04. We're actually getting fairly close. When I divide, I can combine C3, whatever that constant is, divided by 0.04. And I'm going to end up with another constant. So my W is equal to C4 times e to the 0.04 T. And 10,000 divided by 0.04 is 250,000. So I have come up with a differential equation solution, a solution to our differential equation with one constant C4 I need to determine. That's where the initial condition comes in. So W is 300,000 equals, and I'm just going to call this, C4 is fine. I think I'll call it C, so I don't have to deal with the subscript. E to the 0.04 times 0 plus 250,000. Move things away. 300,000 minus 250,000 is 50,000. Equal to e to the 0 is 1, so that is my constant right there. So my actual function, W, is 50,000 e to the 0.04 T plus 250,000. And if we let T equal to 8, because we said that in 2010, which is the worth we want to know, time is 8, e to the 0.04 times 8 plus 250,000. And it usually works pretty well if you start with the 8. 8 times 0.04 equals e to that power multiplied by 50,000 plus 250,000. So the W, the net worth of the company in 2010, is about $318,856. So over 10 years, the net worth has increased about $18,000. Almost $19,000. So this is the net worth of the company. I'm sure you're familiar with Newton's law of cooling, heating, because it can do both. But it is a differential equation because it is a rate at which an object cools or heats, and it is proportional to the difference in the temperature of the object and the temperature of the surroundings. So if it's the rate at which an object cools or heats, let's say the derivative of n, the temperature of the object, with respect to time, so it's a change over time, is proportional to. Is proportional to means a constant multiple of. So if I have a constant multiple of something, that's equal to k times that. To the difference, okay, we've got a difference between the temperature of the object and the temperature of the surroundings. Well, the temperature of the object in minus temperature of the surroundings, A. Now, A is a constant, and it can be a temperature of the surroundings, it can be usual sales, it can be a variety of different things. N is the function, so this is the object, the temperature of the object, or the usual sales. That's what N is equal to. And this formula can switch. Sometimes it'll be A minus N, depending on whether it's a cooling or a heating problem. The standard Newton's law of cooling formula, we say N of T is A plus C e to the KT. And this general formula hits either heating or cooling. So it all depends entirely on whatever the application is that you're working with. So I'll do a couple of different applications and we'll see how this works out. So let's look at this first problem. In this problem, we're looking at an advertising campaign where daily sales for a company were at 6,000 and increased to 10,000 during the sale. At the end of the sale, sales began to decline. So sales declined at a rate proportional to the difference between the present and pre-campaign sales. So that if T is time and days since the end of the sale, at the end of the sale is day 0 and sales were 10,000. S of T is daily sales at that time. So the S stands for the sales at the end, starting at the end of the campaign. S of 3 days later, we were told that sales were already down to 8,000. Let's see if we can set up our differential equation and then see if we can get a formula to find out just what's going to happen after this time as it continues, sales continue to drop. So sales decline at a rate. If my daily sales are S of T, then the derivative of S with respect to T is K times. Remember, the proportional means some constant times that. The difference between the present and pre-campaign sales. The present sales, the pre-campaign. Pre-campaign sales, that's the usual sales. And the usual sales are $6,000. So that's the usual. It was higher and it's going down. So we have our sales at the end of the campaign are dropping, so the usual sales are less than that. It's really important to figure out where the S goes. Is it S minus 6,000 or 6,000 minus S? Since S is beginning at the 10,000 at the end of the sale, and dropping, then the 6,000 is a smaller number and has to be subtracted. I have a differential equation to solve. I have to separate the variables because I have some function k. Well, we can call k a function of t because it's a constant, and this parenthesis is definitely a function of s. So we have a product, so we can solve it by a separable differential equation. So I keep the ds on the left and divide through by my parenthesis. Set it equal to, and I keep the k, always keep constants on the right, and I multiply across by dt. So when I do the antiderivative, I'll have natural log s minus 6,000 equal to k times t plus c sub 1. Well, we've seen this before. This is fairly common as far as the growth with something or decline. So I do the e bit, and I end up with my differential equation going down as far as the solution. I almost have an s. Not s equals s minus 6,000 equals, remember how the c moves to the front? Call that c e to the kt. So I don't know c, I don't know k, s is my function, but I'm pretty close because I've left out a few things since I've done something similar earlier. So I add 6,000 to that side, 6,000. Now, as a reminder, how I got my c in front, e to the kt times e to the c sub 1 can be done because of rules of exponents. So my e to the c sub 1 is what became my c over here. This is all I can do for now, so now I must use my initial conditions, and that will help me solve to get the information I need. So let's move some of this. My initial condition says that when t is equal to 0, sales are 10,000. That's S. So for t equal to 0, I have 10,000 for my S equal to C e to the k times 0 plus 6,000. K times 0 is 0, e to the 0 is 1, C is equal to 4,000. So my differential equation my solution at this point is S of t equal to 4,000 e to the kt plus 6,000. So I've used my first condition and have a value for C. Now I move to the second condition. And if you have two conditions, always use t equal to 0 first. So if t is equal to 3, S is 8,000. So that's equal to 4,000 e to the k times 3 plus 6,000. So I'm getting a little bit closer every time. I want to isolate the e to the k part because that's the next variable constant I need to solve for. So I have to subtract 6,000 first. Gives me 2,000 equal to 4,000 e to the k times 3. And then I divide by 4,000. 2,000 over 4,000 is 2 over 4, which is a half. And now I'll take the natural log so that I can solve for that. I take the natural log of both sides over here would be natural log of a half or 0.5 equals natural log of e to the k times 3, and the ln and the e are inverses, so I have k times 3 equals the natural log of 0.5. So when I divide by 3, I find that k is equal to a negative 0.231. Put the k back in. What was the last thing I had? Right up here. If I put K in here, I have my formula S of T equal to 4,000 e to the negative 0.231 plus 6,000. And so this is the solution to my differential equation. Left the T off the end. There we go. And I can find the sales at any time T. This is at the end of after the end of the campaign. So this is my formula for my sales problem that I started with, the advertising campaign. In this problem, we have a new DVD that's just been introduced to the market. And the question is, how many can we expect to be sold in a year? Well, one of the issues is that the sales are expected to level off at 50,000, so we do have an upper limit that we can expect. And it says that sales increase at a rate proportional to the difference between the saturation level and the sales up to the saturation level. So these words here tell us we have Newton's law of cooling. So if I write a formula just from this piece, T is the months since the introduction of the DVD, N is the number of DVDs sold. Sales increase at a rate, so that means the change in the number over time is proportional to the difference between. So that's when the parenthesis opens. The difference between the saturation level and the sales up to that point. Saturation level is 50,000. And if it's sales up to that point, then the number of DVDs are smaller than the saturation level. So we have to put this first. This is different from the previous example. So we have 50,000 and we're going to increase up to that point. This is a heating problem. Now, I can do this as a separable differential equation again. I can move my whole parenthesis under the N, under the dN. Leave the constant K where it is and multiply by dt. So when I go to do my antiderivatives, I have to look at this. But note there's something different here. Since I'm subtracting N, it's not like the last example where it was just N plus a constant or S plus a constant. If I do my U du here, I do have an issue with the problem with the negative sign. So I do have to think about what I can do with U substitution. So my U here of 50,000 minus N, du for this one is negative 1 dt. So I have to account for a negative sign. So we'll have to put a negative in and put a negative in front. So when I write up with U, I'll have a negative 1 times the integral of 1 over U du equals the integral of k dt. So I have to accommodate this negative sign. So when I integrate, I have negative natural log of U, and I move the plus c to the other side, equals k times t plus c, call it C1. And I put in my negative sign, ln of my 50,000 minus n equals kt plus C1. Now when we go to solve this, because of this negative sign, it has to go first. Remember, what we're trying to do is get to the n, have to get inside there. These are not short problems. It is what it is. So the negative sign multiplies across first. So my natural log of 50,000 minus n is equal to negative kt, and I like keeping the plus c, so I'm going to multiply negative C1 and give me a positive C2. And to get my ln gone and my exponent in the right place here, I have to do my exponentiation thing. And I end up with 50,000 minus n equal to e to the negative kt, and this can split up to give me my second multiplication of e to the negative kt times e to the c2, which gives me c e to the negative kt. And I can solve for n. So I've got negative n equal to c e to the negative kt minus 50,000, but I want n. So n is equal to negative c, let me make that, what was that, c2 down there? Let me go back and make that c3. E to the negative kt plus 50,000. And the reason I decided to keep my c3 as a new constant is my negative c3 now I'm going to call positive c4. So n is, let's just say c, e to the negative kt plus 50,000. Now I almost erased my condition here, but notice that this is at 2 months after the beginning. So I don't have a 0. So we start with plugging in t equal to 0 to give us a constant. But remember, it's a new DVD on the market. So because it's a new DVD, that indicates that at time 0, sales were 0. So I do have a value at the beginning that I will use as my first condition. You don't pretty much ever start with t equal to 2. At least you don't if you can avoid it. So n is 0 when t is 0 plus 50,000. E to the 0 is 1, so c is negative 50,000. I have to subtract over here. That's my c. So my function, my actual solution here for this part is here and here. N equals negative 50,000 e to the negative kt plus 50,000. And we don't really, that's kind of a messy way to look at it. So let's go back and rewrite that as n equals, and put the plus first, 50,000 minus 50,000 e to the negative kt. So I've used up my initial condition. And I have a formula now, except I still don't know k. My 0 time gave me my c value. My k is still missing, so I use the next condition. So after 2 months, there were 10,000 DVDs sold, so n is 10,000, equal to 50,000 minus 50,000 e to the negative k times 2. To isolate the k, start the farthest away from it. I need to get my 50,000 to the other side, which gives me negative 40,000 equal to negative 50,000 e to the negative k times 2. And I divide by my negative 50,000. 2 negatives make it positive. I have, well, I'll go ahead and put this down here, or up here. Negative 40 divided by negative 50. 4 over 5, 4/5 is the same as 8/10. So when I take my natural log of both sides, natural log of 0.8 gives me a negative k times 2. When I divide by negative 2, which gives me k equal to 0. I think there are 3 ones here. Might just be 2. I think it's 0.111k, 1116. So that's my value for k. I go back up to the formula, up to here is what I had, And my formula then for n is 50,000 minus 50,000 times e to the negative k t. So this is the formula that I've got. Now, both of the last problems that I've done in general, n was equal to a plus c e to the kt. But you do have to find c and k. A will always be given. You just have to figure out which number is the a. It's the usual number, or the surrounding temperature, something like that. The question here, there was a question, how many in a year? So I have to now put t equal to 12. So when t is equal to 12, you put it in, be very careful, because now I have to multiply negative times that, raise e to the power 50,000, and then don't forget the subtraction. And we end up with the number after 12 months, because this was per month, is about 36,897. So it started out with nothing. After 2 months had 10,000, and then after 12 months it had increased to almost 37,000. So this was the number of DVDs. This example, Newton's law, was a heating up process because sales were increasing. An earlier one was a cooling process because sales had decreased at the end of a campaign, of an advertising campaign. So you set up and you figure out what you need to use. You've seen a logistic function before. We're now going to look at logistic differential equations and see how the words give us what we need to then get the formula for a logistic function. The rate of change of a quantity n, rate of change of n, is proportional to the product of the quantity n and the difference between the quantity and its limiting value. You'll note that the words seem to be getting longer. So let's go back and take all these words and put them just into a math equation. Rate of change of quantity n. Okay, this is dn dt. So it's over time, so it's with respect to t, is proportional to, equals k, to the product. Okay, we have things to multiply here. The product of the quantity n and the difference between the quantity n and its limiting value a. Okay, think about it. It's a limiting value, so if it's the limiting, then a is going to be the highest number. So the a comes first, and we subtract n. That's what our logistic equation does. It increases and levels off. Now, unfortunately or happily for you, we did not do the type of integration formulas that let us integrate this. But we do know what the results are. N of t is equal to the limiting value a. You may at some point have called it m because it's the maximum, over 1 plus c e to the negative a times kt. So the a is actually in two different places. You may have been familiar with it as the e to the negative rt, and I'll show you how we can get to that after we do one of the examples. So if this is what you have for your differential equation, this is the result of it. It's a single result. And we're going to do two problems that show two versions of this. This example tells us about a flu outbreak on campus, which happens every year at great universities. And so it increases rapidly. And N of T is a number of infected students. When the flu first was noticed, 15 students had it. 4 days later, the number was up to 50. So T is in days. And there are 20,000 students on campus. So since this is logistic, and you'll be told if it's logistic, then we know that in general the formula would be dn dt equal to k times n times a minus n, but we can't solve that. So we have to go directly to the formula. Okay? And the formula for n of t is A over 1 plus C e to the negative AKT. When I wrote the differential equation, one thing I want to point out, the A, the upper bound, is the 20,000 students. So if N is the number of infected students, 20,000 minus N is the number that are not infected. So as the flu continues, the number of infected multiplied by the number of non-infected is what gives us our rate of change and how we can, if you knew the calculus. And the integration is shown in the lesson to get this formula. But that's the uninfected multiplied by the infected. Well, let's see what we know. We know A is 20,000. That's the maximum number of students on campus. So N of T is 20,000 over 1 plus C e to the negative 20,000 times K times T. That's what I put in for my formula. So I have to now start using my conditions. N of 0 is 15 students. N is 15 when T is 0. And negative 20,000 times K times 0 is 0. So this is e to the 0, which is 1. So I have 15 equals 20,000 over 1 plus C. I multiply across. 15 times 1 plus C equals 20,000. And if I take my 1 plus C, I can do 20,000 divided by 15. And then I subtract 1. So my C value ends up being 1332.3. Okay? You do the division and then you subtract 1. Now some people multiply through by 15, but I tend to just divide first. That's our value for C. So I can go back up to where I had my formula here and put in my C value. So let's back this up a little bit more. I want to leave that one condition in there that I haven't used yet. So my N that I have is now 20,000 over 1 plus C 1332.3 e to the negative 20,000 times KT. And my next condition says that when N is 4, I have 50. So 50 students after 4 days are the number that has the flu. So you continue. And I expect you've done a lot of this parts before. I have negative 20,000 times K times 4. So, I'll wait on that. My negative 20,000 times 4 would give me negative 80,000 times 4. Multiply all this across. 50 times 1 plus 1332.3 e to the negative 80,000 times K equals 20,000. I divide through by 50. One of the zeros goes, one of the zeros goes. 5 is 400. That's 400. Subtract 1, I get 399. divide by 13 point, this number. I have trouble with that number. Subtract 1, 399, divide by 1332, ends up with 0.2995. Take the natural log of both sides. That's not below it, it's up here. And do the divide by 80,000. K would be ln of 0.2995 over negative 80,000. And K ends up being 0.1234 zeros and a 1 and a 5. K is a tiny little number. Big formula. You have to put that back in up here, multiply by the 20. We'll plug our 20,000, excuse me. Oops, 4. Let's see what we've got up here. Ditch this, 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 and this. Oops. One plus 1, 3, 2.3 e to the negative, I have forgotten. Okay, so I have to put it all back in here. 20,000 times K, which is 0.123415, and then times T. So once we get to this point, finally, we can plug in T equal to whatever we want to. We asked for 2 weeks, so we'd plug in T equal to 14 and end up with about 953 students. Remember, you can get a decimal, but you've got to round because students are integers. They're not fractions. So this is a lot of messy numbers, but typically this is what you have to do when you have data and you have to come up with a result. This is the general form of our logistic differential equation. The rate of change is proportional to the product of the number and the difference between the limiting value and the number. But there's no R in here. We don't really know what the rate of change is, what the rate of growth is. So we can fiddle with this a little bit algebraically, and I can come up with a formula that actually uses R, which is our rate of growth, which is the more familiar logistic formula for you probably. So I'm going to leave K where it is. I'm going to move that N to the other side. And then I want to factor the A out of here. K times A. When I factor the A out of here, I get a 1 minus. And if I write this piece as N over A, you can see when you multiply back times the A cancels and you've got your N back. So this is another form of a logistic differential equation. The thing that's nice about this is that K times A is the growth rate. So this differential equation is the same as R times 1 minus N over A. And remember, A is the constant. That's the limiting value times N. And so from this, I have another formula that I can work with that uses R instead of the A times K that is such an issue when you're trying to solve the problem, trying to find K. So N of T, the result, is equal to A over 1 plus CE to the negative RT. So this is a little less complicated, but you do have to have a way to get R. And in problems where you're given the growth rate, you can go directly to this form. So it makes it turn out to be a much nicer type of problem. So let's look at an example that uses this form and gives us a growth rate. So we have a hiking club, and M is the membership, in 100 members. So that at time 0, there were 100 members in the club. When they decided to form a club, there were 100 people, and we said, let's have a club. So at t equal to 0, there were 100. Now, notice that the 100 is in words, so that means that the value for m will be a single number, and then you'll have to add 100 on to the end of that. Okay? The membership changes by this formula. dm dt, that's the change in membership, is equal to 0.19 times 1 minus m over 10 times m. Now, when we first looked at the differential equation, previously it had dn dt equals r times 1 minus n over a times n. So you need to reconcile this differential equation formula with what you're given here. So r is 0.19. A is 10. Now, since it said A is 10, that is a membership, so it's 1,000. So that would actually be 1,000 people. That's the upper boundary for their membership. So using these numbers, I can work in here and see what I can come up with. So, this case, it is m of t equals a, which is 10, over 1 plus c e to the negative 0.19t. Now, this dm dt is also the same as the derivative, so sometimes you may find that written as m prime of t. It's a rate of change, it's a derivative. Well, with this information right here, the only constant that I don't know is c. So hopefully our initial condition will give me that value. So m is 100 equal to 10 over 1 plus c e to the negative 0.19 times t equal to 0. M of 0 is 100. So e to the 0 is 1. So I now have 1 multiplied times 1 plus c equal to 10. If 1 plus c is 10, c is equal to 9. So my formula now, m of t is 10 over 1 plus 9e to the negative 0.19t. And depending on what I'm interested in, I can find out how many members they can expect at any time t. And I did not mention t is in months. So if t is in months, maybe I want to know after 9 months what the membership is, or 12 months, 1 plus 9e to the negative 0.19 times 9. Do all my multiplication, addition, division. Very careful with the signs. And that number turns out to be about 3.8055. So does that mean there are only 3.8 people after 9 months? Now remember, this is 100. So the actual membership in the club would be 100 times this, about 380, 381. Remember that actually if you do 380.55, you don't have enough to make another person, so you drop it. So the membership would be about 380 people after 9 months, but the M value is 3.8.